Hello, today we're going to talk about true and false. And so for true false, remember, you guys are going to have to do justification. So I'm going to put justification on here for each of my answers. And kind of some of these questions are probably a bit harder than our true false justification because if you add in justification. But this is just so you're comfortable with it. One thing I really want to emphasize that if you guys get some of these wrong, make sure you're documenting what kind of mistakes you make so that in the future, you're going to be able to learn from those mistakes. If you just look at the solution or listen to me, my nasally voice wash over you, you're not going to get a whole lot out of that. So, without further ado, let's kind of get going. Okay? So, question 1. 2 ways you can approach this. Both work. 1, truth table. 2, simplification. I think truth table is a little longer and makes sense, so I'm just going to do the just simplification. Okay, R and not R. So I have P implies R and not R. That's like P implies false. Implies not P. This thing here is going to simplify down. So if I have something implies false, that must imply that it must be. That's equivalent to not P. If you don't believe that P implies false is equivalent to not P, do a quick truth table. One way to explain this, you can think of implication as like a promise, right? I promise that if P is true, then Q will be true. And so if your end result, you didn't do the thing you promised, well, the condition for your promise must not have happened. Okay, so we get P, not P implies not P. This whole thing here is going to evaluate to true. If you don't trust that part, do a truth table. Both of these are 2-line truth tables, so they're definitely doable. And they're just as doable as doing the 2 values of P times the 2 values of R, and just mapping out all the possibilities that way. Okay, we have question 2. Z is an integer, Pi is a predicate. You want to see if P of 0 is true and there being some I, where I is an integer, where P of I and P of I plus 1 are true. If these two things in conjunction imply that this property P, for all I in Z, I just need to, I being greater than or equal to 0 implies P of I. So I'm going to do this by a counterexample, which is sufficient justification. But I'm also going to explain why this doesn't work. Here, right here, we have a there exists. And a there, if we tell you, right, that this was a there all, then this is the idea behind induction. If I know my base case works, and I can show that my inductive step works, then I can show that it works for all numbers greater than 0. In this case, however, we don't have that kind of inductive step. We just know that the inductive step works for some value of I. So for example, let's say P of I is defined as I being less than or equal to 10. Then we have this works, P of 0 is true, and P of 1 is true, but P of 11 is false. And so we have both the conditions we had on top, but our answer still evaluates to false. Okay. Next, 3. 3 and 4 are more predicate questions, which are very closely related to each other. So I'm going to talk about them in one go. Also, I'll bubble things in. This is true. This is false. This is... Okay. We have real numbers and rational numbers, and we say for every pair of rational / real numbers. If x is less than y, there is some number z between x and y. Now, for this, there's two ways to look at it. One, think, okay, can I come up with that number? Turns out you can't. Just take the average. So for all x, y, which are real, x plus y over 2 is going to be real too. And this is also true for the rational numbers. Oh. So here, right, this thing is true for the reals and the rational numbers. And so if I take these values as z, then I can show that these things hold. Okay. One, I guess, other way you can think about it is that there are no two rational numbers or real numbers are going to be next to each other. And so that is the reasoning why both of these are going to be true. Okay. Next, any stable, stable marriage. Peep's taking it in the summer, right? Summer 2019. Don't worry about this. We didn't cover it. My future friends, we're going to cover it like this. Okay. So I have, let's say 1, 2, 3. Can I use this 1 or 2? Yeah, I can use this as, no, let's just do 3. A, B, C. So let me just draw a line and say this is number 5. And so this is cool trick on a blackboard you can do to get a dashed line that looks so cool, but I can't do it on this, which makes me sad. Can't show off. Showing off is fun in terms of blackboard tricks. Okay, here I'm going to define my preferences as follows. So when you're constructing counterexamples, it's really helpful to say, okay, so this is arbitrary 3 people. I have 2 scenarios I want to work with, right? So I want this to be the one where A is, let's say our numbers are our men. In this scenario, I want A to be happy and B to be happy. That's happy. Happiness can look on different faces. And in this scenario, I want A to be happy, as he can be, but B is not. B did not get the optimal pairing that they got in the left example. But both of these are going to be stable. So this is my idea. Before I actually solve this problem, I have this idea of saying, okay, I'm going to say it's possible for B to do better, but B can also not do better while A still gets his best thing. So I'm going to say A wants to be with 1 more than anyone, and A is going to get it in this example. And B wants to be with 2, and B is going to get it in this example. Okay. And so here I'm like, okay, A wants to be with 1, he gets in this example. And what I'm thinking now is, for this one here, how am I going to construct my example so that B, let's say, gets 3, and it's still stable? Let me just do. Okay, that looks a little messy, not gonna lie. That's okay. So I want B to be able to match with 3, who is worse than 2, but I want this whole thingy to be stable. Okay? So I'm just going to say, okay, I want you to be stable, so that's fine. But 2, I don't want 2 to be a row couple with B in the right case. So I'm going to say 2 really doesn't want to be with B. So 2 prefers, let's say A is greater than C is greater than B. Okay? So 2 when he's with C is more happy. But C prefers 3 and 3 prefers B. So here we have A is greater than B is greater than C, right? And so in the right example, A gets his optimal pairing, but the numbers in this case are happy. In the left example, A still gets his optimal pairing, but the letters are happy. And so after I do this, this is like the core idea behind my example. Actually, just this right here is the core idea behind like how I came up with this. This is the problem solving process that went through my mind as I solved this problem. And after I get this on here, I'm just going to fill in the rest. Oh, doop. 2 greater than 3 greater than 1 greater than 3 greater than 2 greater than 1. And A is the greatest. A, B, C. And now I have an example that works. There are numerous other examples that you could come up with. And if we actually did TFJs, this is probably it's like a long TFJ. So don't worry about questions of this length. But I just want to talk about how do I approach problems that require you to come up with an example or counterexample. And really what I'm doing is I'm saying, what do I need to make it work? And then I'm filling in the rest. So see, I got those drawings out. I drew first this part here is like my basic idea. And then the rest of the stuff here, I was like, okay, filling in like some examples. And then I made the preferences to match that. And even if you're not doing stable marriage on your exam, this is like a good way to think about things and how you might approach problems. Any graph with no two triangles is colorable. Okay. I'm going to think about this the same way we're thinking about our last example counterexample thing. Okay. So this is false. Also, one thing I don't know if I said. Why does this mean it's false? Think about it for a second. Pause if you need to. So here, this pairing, 5, is optimal for all men. Here, it's optimal for A, no longer optimal for B. And so I've shown this kind of dichotomy. Okay, 6. Any graph with no triangles is too colorable. I'm going to approach it the same way. I'm going to say, okay, if there were to be a counterexample, I'm not sure that there is, but if there were to be, I'd probably have a square in there. Okay? And I can have a triangle. So what if I had another square? Oops. That's a good point. I make a second square. And what happens? 1, 2. This has to be 2. This has to be 1. Has to be 2. This has to be 1. It works. And I'm like, okay, why did this work? Well, this doesn't really help me. And I'm like, okay, what if I did this? Boop. That sure ain't a triangle. But now I have a nice property. This one, I can't do color. So what was the idea behind me kind of going for this? I at first just drew 2 squares. But the 2 square counterexample, it didn't work. And for the true-false justification, sometimes for a timing perspective, it's better if you don't see like how you might construct a counterexample, just skip it, move on. But here I was like, hey, so these just kind of fit, but I could make it not fit if I just took this edge and put it over here. And there's no way I can color this. Because this must be 1, these must be 2, these must be 1. So this has to be 2, but it also can't be 2 because it's adjacent to a 2. And I have no triangular faces. Okay. 7. Graph with average degree 2 doesn't have cycle. not cop out, but easy way to solve this. Trees are the maximally connected acyclic graph. Okay. So you can use this property. Yeah, I should make sure. There will be an annotation in there to see if we prove this in the notes. But what you should do, just to make sure you're confident in yourself, if you have time, is you should. Okay, why is it true that trees are maximally connected acyclic graphs? It's because, let's say I have a graph which has so trees are the acyclic graph, are connected acyclic. This you can if we have a disconnected graph, oh god, my handwriting's atrocious. I mean, from regrades, or from grading, some of yours are worse, but that's okay. You're not a TA, and I am. But this thing is hard to write with. If we have a disconnected graph, well, what does that mean? Each component is a tree. If each component is a tree, then this is going to have fewer edges. So you can essentially prove that trees are the maximally connected acyclic graph. But whether you prove it or we proved it in the notes, which I will double check for you guys, I personally think that if it's some sort of true-false justification thing, or it's a short answer, it's probably a little bit long for true-false justification. Not for a TFJ, but this is like a short answer. Ooh, spinning wheel of death. Okay, we're good. Okay, then it's just safe to prove it. Doesn't take too long. For average degree, that's going to be 2 times E over V. This whole thingy is 2 times V, and I'm just using this for cardinality of sets. This thing is going to be less than 2. And so, the maximally connected, the acyclic graph with the most number of edges has less than average degree 2. More edges implies that it's cyclic. Okay. And okay. Next, length of any Eulerian tour of a graph is even. Is there any other profound wisdom that I can give you? No, because I have none whatsoever, ever. Now, on a more serious note, for this one, it's like understanding what an Eulerian tour is, and then understanding that like the length of the Eulerian tour is just going to be, number of, is not going to be related at all to the even like you can have an Eulerian tour, it's just number of edges, so it's fine. Okay, I will clean this out. The Eulerian tour is just going to have the length number of edges. Edges does not have to be even. The total degree does, but that's because it's 2 times the number of edges. So triangle works. Okay. 9. Program takes P, input X, steps S. So let's call this d of pxs, and returns yes if p run on x halts and s steps. So this is the whole steps versus lines thing. I can count the number of steps. Once I'm done with that number of steps, just I'm done. Okay? I can do that. I'm allowed to. Why am I allowed to? It's because after I finish s steps, that will happen in finite time, and I can just stop executing the program and just give the result. IntelliJ Debugger does that. You can have a program that loops forever, but if you take s steps, you can see, am I still looping or am I not? So this is the IntelliJ argument. I can execute for s steps and see if it has terminated yet or not, and return that result. If IntelliJ Debugger can do it, the program can definitely do it. IntelliJ Debugger is not a gift from God, unless you have a 61B project, in which case it is. Okay. One can write a program that solves the program P using the halting problem as a subroutine. Then the problem P is undecidable. So this one, I want something that returns yes. So I'm going to say Q returns yes. That's all Q has to do. I can define Q using halt. Q and it returns halt of print with the letter A. We know that print halts for a string, a finite string input. And so halt is going to return yes, and Q will return yes. There, I can implement this by just saying yes. Both of these are valid ways to define Q. Just because I can use the halting problem does not mean my problem is incomputable. Bijection between power set of rational numbers and the real numbers. Okay. Running low on space, so this should be fun. I'll just do some of these on here. Okay, power set of rational. So, for this one, right, we said that we would, I think power sets were optional, so we would define them if we ever used them. So, one very helpful fact about the power sets, you can do power set of the natural numbers, or power set of the natural numbers is going to be uncountably infinite. And how do you do that? There's a bijection between the power set. Okay, I don't know how to do the power set symbol. Power set. Can I just copy and paste this little like string here? We'll see. Power set of n to infinite bit strings. Whoa. How? For each element of S, so let's call my bit string B. B, so F of B is the set which has these properties. Or I should say, it's X for all X and N if B sub X, so the X character of B is equal to 1. So that's how I get from counting numbers and natural numbers to infinite bit strings. Infinite bit strings to reals at any uncountably infinite covered. How do I get from power set of q to power set of n? Take some subset of q. Apply the bijection, or a bijection, I guess, from q to n element-wise. Uh-oh, I'm out of space. Sad. Element-wise. Why does this work? This is going to work because, let's say I have something like 1/2, 0, 1. And let's say I tell you that the way we've done this bijection, this maps to, element-wise, 1/2 maps to 3, 0 maps to 0, 1 maps to 1. That's how our bijection works. If that's the case, then this is a subset of n, this is a subset of q, and it's a bijection because I can just apply the inverse operation to go back and forth. So this is going to be true. So I know power set of n is uncountably infinite because if I say bit strings uncountably infinite, I can go from power set of q to power set of n to infinite bit strings to reals. Okay. In just the time, I'm just going to move on. I don't know why I'm saying that. It's a video. I'm alone. That's depressing. Okay. This thing. Before I give you the answer, when and only when is this true? So it's only true if A and B are disjoint. Otherwise, it's equal to this. If A and B are independent, this term is going to be equal to probability of A times probability of B. But it's not going to be equal to 0 unless probability of A or probability of B is equal to 0. For 13, there's the slow and tedious way, which they actually solve it, and the faster way, which is say probabilities are different. So let me go slow, find two probabilities. Find two probabilities. The first probability is that second bin is empty. And then first or second empty. This isn't slow. I shouldn't call it slow. So this thing, second bin being empty, I can just do counting to say the remaining 9 bins, there's going to be 9 options. This is the ways we can put the other balls into the other bins out of this many total. Second given first is going to be a intersection B over B. In this case, our denominator is the same thing. First bin being empty. Our numerator now, though, is going to be first and second being empty, which by a similar argument is just this. If I take these, if I simplify this down, I get this. This is actually, like, this is a good method to use. Okay. How should you review these questions? Me just, like, saying these things at you, if you just look at the true and the false, the end result, doesn't help you. What does help you, document what areas you got wrong, what kind of questions. Go through the rest of this test, document exactly what areas you got wrong. Use that, figure out what are your weak spots, what are your strong spots. What's the area you're struggling with? Do I have a single piece of spare room? Let's go to the top and erase this stuff. There's, I think, 4 broad areas to kind of taking a 70 test, right? Content. Precision. Time. Shoot, what's the first one? Content, precision, time, and I guess how do I put it? Pathing? Problem solving. Problem solving is too vague. More specifically, it's trying out possibilities. It is problem solving. What I mean by that is more specifically coming up with possible ways to solve a problem. Like, what kind of methods or techniques might we use to solve this problem when you see a problem? It's not just like, oh, how do you solve a problem? Because that also has, you need content, you need precision to do that. It's very specifically, I see a problem and I try to come up with how I might solve it. And then how you approach the solution, things like that, it's like different skills. If you're feeling you didn't know just some facts, review discussions, review notes. If you're feeling your justifications would have gotten you destroyed for like a short answer or like TFJ for a short answer. Just make sure you look at how we word things, how we're precise. See what like subtle mistakes you made. If timing is your issue, just look at what are you spending too much time on. Time yourself when you're asking questions. Look at look at your time in the middle of the exam when you finish like a chunk of the exam and say, okay, I spend way too much time on long answer, not enough on true false or something. Our balance is different, so also look at how you've done midterm 2 for something like that. This last thing, the problem solving aspect, that's going to be whatever you got wrong here, see what methods you use in their solution, write the ones you did not come up with on your own, you were unable to come up with, and document those for all, like as many tests as you can, and come up with your own personal bank, organized, it should be organized in some way, a way that makes sense to you of problem solving techniques, and also some notes on when you kind of apply them. And when you're approaching an exam, try to understand the problem solving techniques that you can use. And other people have posted like stuff on Piazza about like their way of interpreting this 4th one. But like think about these 4 areas of test taking and doing well on tests. See where you kind of struggled for this whole test and kind of like move on from that. Yeah, it's my general studying philosophy.